Greetings, colleagues. Welcome to SAMPI's Advances in Non-Destructive Methods for Space Vehicles, Technical Committee webinar. Greetings. Please join our webinar. Thank you. If you can, in the chat, please place your name, your company name, and your geographic region so we get to know each other. Again, in the chat, please enter in your name, your company name, and where you're located geographically. Thank you and welcome to joining the Advances in Non-Destructive Methods for Space Vehicles webinar. The Space Applications Technical Committee leadership is Dr. Chris Fleming from Northrop Grumman. The Vice Chair is Dan Polis from Sierra Space, and the Secretary is PhD student Jaden Palick from the University of Nebraska-Lincoln. We encourage you to join a technical committee of your liking. The technical committees are available on 365. It's a virtual committee. You do not have to be a SAMPI member to join. So we really encourage you to join and consider leadership opportunities in SAMPI technical committees. We have Composites Factory of the Future, Bonding and Joining, High Temperature Materials, Recycling of Composites, Rapid Manufacturing of Composites, Thermoplastics, and Space Applications. So again, you can go to the SAMPI 365 page to join. The State of the Technology Industry Report is available for download. It's a complimentary report that the technical committees put together. Each technical committee outlined the emerging trends that they see. Please, again, download your copy from the SAMPI online store. Website is included at nasampi.org. Webinar sponsorship opportunities are available. Please contact my colleague Jordan at sampi.org. That is Jourdan at sampi.org. Thank you so much. Here's the lineup of the webinars that we have completed. All webinars recordings will be available on SAMPI YouTube page and also on the resources tab of SAMPI 365. We encourage you to once again to download, to view the webinars after and prior on the SAMPI YouTube page. Welcome once again to the SAMPI Space Applications Technical Committee webinar series. Today we have Dr. Eric Burke from NASA Langley Research Center. He will discuss advances in non-destructive methods for space vehicles. Again, please in the chat, enter in your name, your company name, and your geographic region so we get to know each other. In the chat, please enter in your name, your company name, and your geographic location. We will be starting momentarily. Our moderator today is Dr. Dan Polis of Sierra Space. Thank you so much. Space Applications Technical Committee leadership is Dr. Chris Fleming of Northrop Grumman. Vice Chair is Dr. Dan Polis of Sierra Space, and Jaden Palick, a PhD student at University of Nebraska-Lincoln. We encourage you to join a SAMPI technical committee. All information is available on the 365 page. Please take a look on the SAMPI 365 page. The State of the Technology Industry Report is also available for you. If you haven't had a chance to download it, please download it at no cost from nasampi.org. Webinar sponsorship opportunities are available. My colleague Jordan at sampi.org is managing that. Please feel free to send Jordan an email, Jourdan at sampi.org. The webinar series that the Space Applications Committee has put together is started back in October, and we have one more coming on February 14th. We hope you will mark your calendars and join us. I'm going to turn it over to Dr. Dan Polis now so that he can start to introduce the speaker. Thank you, Dan.
Thanks, Raj. And thanks everybody for joining. I think we've had a really great series with kind of involvement of some great NASA technical experts. And today we're lucky enough to have Eric Burke. He joins us from NASA Langley. Eric currently serves as the NDE program manager for NASA's Office of Safety and Mission Assurance. He's been part of the NASA community for over 15 years, focusing on development and application of innovative materials and technologies. He's also in his side job the NDE subject matter expert for additive manufacturing, a hot area, as I'm sure all of you are aware. And he also leads the Small Business Innovative Research and Development Program for technologies that will apply to future inspections of the International Space Station and deep space missions. Eric's received national recognition in the area of NDE and technology development, including NASA's Early Career Achievement Medal, the Launch Director Award, and a Silver Snoopy Award. Prior to joining NASA in 2010, Eric worked as a research and development engineer for United Space Alliance and the University of Dayton. Eric holds a Bachelor's of Science degree and Master's degree in mechanical engineering with a focus on solid mechanics. So please welcome Eric, help me welcome Eric Burke for today's seminar. A few reminders. First, please enter your questions in the Q&A and we'll hit those at the end of the seminar. For those requesting charts, the presentation will be published on SAMPE's website in a couple weeks, so the video will be available. And just a reminder that we're recording the presentation today. So with that, Eric, thanks for joining, and it's all yours.
Yep, no problem. Thanks, Dan. So I'll get started here. I'm going to kill the camera just to save some bandwidth. Let me get the screen going here. And I know on my computer setup here, I won't be able to see things, so I'll have to count on you guys to relay back to me, but we'll get her going and make sure that it all works. So I'm going to start this up, Dan. If you can just give me a thumbs up that you guys can see what I think you should see.
Yeah, we got it.
All right. Well, let's get going. So I know we're probably going to be getting close to the end of the hour as we kind of move through this, but you know, no team is you know, without others that help. So I have to mention at the beginning a bunch of people that have helped us along the way. So as Dan said, I'm the Office Safety Mission Assurance NDE program manager, but I also work here at NASA Langley, and about half the time I'm also working for the NESC. So I have to thank Jeanette Plant, who is the program executive for OSMA that kind of oversees several areas and you know, for OSMA, including the non-destructive program. Dr. Bill Prosser, who is the NESC Technical Fellow, Dr. Justin Jones up at Goddard, Miss Erin Lanigan at Marshall Space Flight, Dr. Doug Wells at Marshall Space Flight, as well as Karen Taminger, Zoe Alameda, and AJ Costi at Johnson Space Center, and as well as many others that I just couldn't get on this slide. But to the team, thank you very much. It's always kind of like to fire up this video here at the beginning, just so you guys can get a feel for what we're looking at with space. So it's a big year for us last year. I'll let you watch the video. Yeah, so just in case anybody was just waking up from lunch or the coffee was wearing off, you know, we get pretty excited. And I play the video just to let you know, so we actually got the flight up in the air and it went around and was a, very successful mission for us. So very exciting. But a lot of that work started back in 2016, working both with Langley and Lockheed Martin company, we developed some inspection systems. So what you've got on the screen there is a shot actually in the OMB at Kennedy Space Center of the terahertz system that we developed to actually scan the avcoat that's on the heat shield. It was a full application, but we also work with, and keep this in the back of your mind because we're going to talk about it a little bit more later, using a terahertz system that was developed under SBIR. And so, it's a good application where we're working with the people that are at Lockheed Martin and commercial crew, along with the NESC, to actually get the Orion heat shield put together. And this is actually the heat shield that flew on that mission. So we're very proud of that. And we also were able to use something that was a 3D backscatter system. So this one's a little bit unique, also developed under an SBIR program. So essentially the terahertz was most of the acreage coverage. So on the arm here, you can see there's actually a terahertz head that's scanning over these blocks, looking for voids in the avcoat blocks, even through the plastic here. And so that's the acreage coverage. But of course, there's joints in this heat shield. So in the joints, the terahertz didn't work very well. So we actually came up with working through the SBIR program with Physical Optics Corporation, a 3D backscatter unit. We had it here at Langley for just a couple of months before we found the perfect application in actually finding voids in the seams that are on the heat shield. So we took that system that was developed under the Small Business Innovative Research and actually deployed it down to Kennedy and got it qualified with Lockheed Martin. And so it actually just came back here. And so we've been working with it a little bit more, but you can kind of see, so it's, so both the terahertz and the 3D backscatter system will give you three-dimensional data. It does come out in kind of like a CT-like volume, although the resolution isn't quite as good as CT when you have only single-sided access because of such a large object. It's a real game changer as far as being able to look down into the avcoat heat shield and get the information that you need for the certification of the vehicle. I will mention, so we've got the flight that just went up is generally referred to as EM2 or Engineering Manned Flight 2. The next one will be EM3, and of course, if you've been watching the news, we're going to be delayed a year, but it's something interesting too. And the other thing I'll mention about this presentation too, and it's always interesting because I'm used to be able to see people, but at the bottom of the screen on most of the slides, where this information can be found after the presentation, you should be able to go and find it. So this was actually so we worked on the heat shield, and then we had a couple other issues with the Artemis 1 integration in the vehicle assembly building, which is actually this building here on the left. So after the hot fire, there were some places on the Sophie spray-on foam that needed to be inspected. But this was actually during integration as they were rolling into the assembly building at Kennedy Space Center. So we were actually asked to come down and do some core stage development. And you can see my colleague Ben Spartha here actually using the scanner. So we had worked again through our SBIR program. It just happens that these three happen to be SBIRs, but so we actually got this terahertz galvanometer. So whereas the terahertz system that you saw in the first slide was kind of it's a time domain terahertz that goes straight down. This one actually gives you, for the NDE folks on the screen, a B scan. And basically what a B scan is several lines of information all put together so that you can create a depth image. And it's actually on a really nice hand roller, so you can take it out in the field and actually roll it around and look at it through the Sophie spray-on foam. And we were able to actually help clear the SLS rocket in the areas where final checkout needed to be done, deploying this terahertz galvanometer. So pretty cool. And one last technique that was not developed here at NASA, but was helped to be deployed with them, was actually developed by Aerospace Corporation, and it's a bond verification technique. So they actually were able to show that using some special analysis tools that we were actually able to do bond verification on the avcoat blocks. And again, that was developed at Aerospace Corporation in conjunction with us and was deployed on the heat shield by Lockheed Martin. So again, being able to find, especially kissing disc bonds on those avcoat blocks, because the avcoat material was so attenuative to sound, we give them a lot of kudos and certainly appreciated their help. So of course, EM1 to EM2 flew and came back, and we knew that there was going to be some charring of the avcoat. So while they were working on that, we started looking at NDE techniques to actually look at how deep the charring would be when it came back. So this is actually a sample block that was put up on the Radiant Heat Tower. And again, so this is that 3D Physical Optics Corporation backscatter system again. And it's a nice kind of way where you can see, the three-dimensional information that kind of comes out of that system. So we took the radiant heat block, and we actually have a very good CT of this block. So we knew exactly where everything was, and we were able to show that using the backscatter, which is a field deployable technique, we could actually kind of figure out, how deep that char is on the heat shield when it gets back. So this is a proof of concept. Eventually, this did get deployed, and we'll talk about that some other day. But we actually were able to develop a couple interesting tools along with this. So developing some machine learning techniques, specifically a random forest technique, and going through lots of different sets of data, we were actually able to set up a few different tools where we could intelligently map how deep the char and the virgin avcoat is on that char block that we had using the backscatter data. So we ended up setting up these groups of tools for the users that can show within plus minus about 2 millimeters intelligently and automatically how deep that char actually is. And all of this was deployed out to the Orion team, and they're still in work working through all the data from the recent flight. So kind of nice, and that is a lot of what we do here at Langley. Specifically, we like to develop tools and then deploy them to the people that need them. So if you've got a one-off NDE problem, certainly contact us because we're happy to get involved. So I'm going to kind of switch gears a little bit here. So a lot of what we're kind of looking at now has to do with this technology for a roadmap to the moon and Mars. And if you go on the page, you'll see this is kind of where the different places that we think NDE is going to have a significant impact. So specifically for gateway and really in space assembly and manufacturing, I think there is certainly a case to be made that inspection for assembled structures in space is going to require inspection. Advanced propulsion, and we're going to talk a little bit about that. And then once we finally get out to the moon or Mars and we start building up all of these things out of resources that are already there, or what's referred to as ISRU or in situ resource utilization, those structures, just like here on Earth, are going to need to be inspected as well. And then all of the surface excavation and construction, again, once we get there, is going to require some sort of inspection, and it may even be periodic, just depending on what the service life is. So certainly when I talk about a lot of this stuff, and as Dan mentioned, one of the things I get involved a lot with is additive manufacturing, and I can even give a plug for the next talk, so I'm not going to cover it too much, but NASA has been putting out a lot of information on certification for additive manufacturing parts, and I've got it listed in here, but that's going to be the next talk with Allison Park, who's the NESC lead for that. But it's actually, additive manufacturing, as many of you know, is really reshaping aerospace design and manufacturing, and we're trying to really work with that, but it can be applied to metals, plastics, and habitat. Specifically, for the most part, for NDE, we've tended, at least in the most recent, to focus on the more metallics, the titaniums, Inconels, and things that are going to require fracture critical certification via NDE. But as you know, with additive manufacturing, you're essentially building up parts layer by layer, and that gives you a lot of freedom as far as being able to do really interesting parts and designs. But it can cause some real issues for NDE, and we're going to talk about a lot of that as we kind of move through the next bit here. But you can definitely save a lot of money and reduce the amount of parts that are for limited quantity production runs, which is really common here at NASA. We don't tend to build thousands of anything. We tend to build one or two, and we like to get them right. It can also be used for repair applications in space or here on the ground, and as well as new designs that may help reduce how many times you have to iterate through development time, test, and validation. So I always like to put this one up here. This one really caught my eye a couple of years ago, and it's just a redesign of what people think it would take to build that engine with additive manufacturing versus traditional methods. And I would say it's sporty at best, but at the same time, if you look at the development time to deployment, you're looking at a factor of 2. lead times on hardware from 3 to 6 years to 6 months, and cost savings that are huge. And as we keep moving forward, that's a big driver for us. But also just looking at the part complexity count drop, right? 1 to 5, 2 to 8, and 22 to 40. I mean, the injector nozzle, which we're actually going to look at here in a minute, 6 parts versus 255. So needless to say, additive manufacturing is here to stay, and working on NDE for it is a critical thing here at NASA. So the question becomes, and you can certainly see the timeline here, how fast things are coming up. I mean, we built the first little wrench. This is Butch Wilmore, who ironically actually presented to Silver Stupi. Making the first additively manufactured part in space, just made this little wrench up there out of plastic, to 2021, where we've got Terran R, essentially trying to do a 3D print of a full rocket and put it into orbit. And we certainly know that both NASA and its commercial crew partners are working hard to certify additive manufacturing parts. And there are a couple different avenues for that. But if you extend out even past that, once we make additive manufacturing parts in space, they are going to have to be certified somehow. And especially if we're going to do in-space assembly, I think this is a critical function that we need to start working on now. And we're even going to talk about some of the in-space NDE that's been done and where we need to go. So just kind of for completeness and background, for those of you who aren't deeply involved with additive manufacturing, there's a lot of different defects that can happen as you're building these things up. You can certainly get dimensional warping, inclusions, because you're building layer by layer. This is a powder process fusion void. You can get delaminations, gas porosity, direct energy deposition gas porosity, and certainly residual stress cracks that form in the powder bed fusion parts as well. Just a couple more. So, and some of these we've started to try and make intentionally so that we can pick them up in NDE, but skip layer start-stop defects, vertical lacks of infusion. And then probably the hardest one that we're working with right now are these trap powders. And you can see the very slight grayscale differences, especially with some of the trap powders, that can be very difficult to pick up with the current processes. So this is from Doug Wells, and I think this is a really good, if you guys haven't seen it before, roadmap for an additive manufacturing part that includes a lot of places that are not necessarily NDE specific. So if you're looking for kind of a NASA's additive manufacturing roadmap and how we think it ought to work, this is a good place to go. But I've kind of marked out a couple places here. So right now, as it stands, the red ones are where NDE has kind of found its own. And that's partly in the as-built raw part inspection and the post-build inspection. And so we really need to have a good handle on, exactly how we do NDE at those and what are some of the gotchas that are going to happen there. And we're going to talk about that in a minute. But I certainly see a lot of future in situ inspection and design for inspectability, and we're going to talk about that too. So kind of moving NDE not just from the end of the process where we find the defects, but back up the chain. And maybe even doing some NDE on things like the powder that goes in, or including that in some of the designs that we're using, and we're going to talk about that too. So just for kind of a technical reference, if you're looking for them, these are the NASA standards that are currently out there and available. And there are a couple more coming, like the Additive Manufacturing Handbook. And as it stands right now, the NASA non-destructive evaluation requirements for fracture critical metallic components basically points back to the 6033, the 6030 for NDE. And so a lot of us were involved in writing both the 6030 and the 6033. And I'm not going to talk too much about this today, simply because I know Allison's going to point to it in the next webinar. So if you're interested in the certification of these parts and the NASA standards, make sure you tune into what she has to say. Just a couple more examples here. So this is actually the injector that I was talking about, where you see this huge reduction in parts. So each one of these little injector nozzles is actually brazed in the original part, and the additive manufacturing part, they're just printed the way they are. This was in a JPL heat exchanger, so you can certainly see this super complex structure in here. And another ejector assembly that was done at Marshall, and as well as the Pogo Z baffle, which helps the buffering and the fuel flow along in the fuel line along the engine. Now, part of the reason I put these up here is as a demonstration of how difficult additive manufacturing can make NDE, right? How do we actually go in, and is it possible to actually inspect a lattice like this? Is it necessary? If I've got all of these nozzles in here, how do I go in and inspect most of these, as well as the super complex structure around the pogo Z hold? So it's an interesting challenge from an NDE perspective that, now we can make these things, but can we certify them? And how would you go about doing that? So one of the processes that we've been looking at, and I've kind of got one up here because it's an easy demo to look at, is in situ monitoring for process control. So this was actually a project that was done here at Langley, where we used an infrared camera, and it's actually mapped to the heat signatures, but you can see a lot of different things in here. And this is a weld that we made. Oop, went forward, I didn't mean to. Where we can see the weld starting to come apart, but you can actually, in the different boxes, you can see it's mapping the weld pool, it's mapping the melt pool, which is the before solidification, and then any of the drips and drops that are coming off of the system to alert a user that something's going wrong. Now, what's kind of interesting in this whole thing is that we actually found that during the cool down, if we look back in this area back here during in situ monitoring, there's a good chance that we can start to pick up defects back in here and relay those back to the final inspection team as we kind of move through things so that the NDE team can kind of look at that later. So we started up through OSMA, the in situ project, which is being run by Aaron Lanigan out at Marshall Space Flight Center and doing a fantastic job. Trying to look at how do we correlate this in situ monitoring data to actual NDE data, and how does that work? So specifically, we were looking to use laser powder bed fusion because it's probably the most common of the additively manufacturing techniques that's out there right now. And the question comes is, how do we analyze the defect capabilities of an in situ monitoring system compared to what we would normally do with traditional NDE created flaws? And can we actually make those those problems with off nominal build parameters, and what does that look like, and then verify the whole thing with actual metallography? So we've been working through it. We actually have another SBIR going with this as well, but using the EOS M290 printer to actually make the parts, and recording the AM processes with their tomography system, and then actually looking at it with CT, and then finally doing serial sectioning of those samples to see if we can correlate an in situ known defect to a CT defect to something we can find in a serial section. And so all of that supports the methodologies for in situ that are related to what you'll hear about in 6030, and the certification approach is certainly for the in situ monitoring systems. And even we're still trying to work through exactly how we're going to work all of that into getting a certified system. So what actually happened was kind of interesting. And again, there's this idea that we're going to be building in space, so we need to have these expert systems and build them up. But we actually made intentional defects, and in the CT for the initial ones, we couldn't really see them, which was kind of interesting. And as you guys know, at least the ones that are working in additive manufacturing right now, there is a lot of CT work that is going on. And kind of, at least here at NASA, we've been sort of pinned to looking at additively manufactured parts with computed tomography, because some of the other techniques still need a little bit of work, we'll call it. But the in situ monitoring system at least picked up most of them, as well as a couple false positives. And then when we went through in the RoboMet, it's 100% hit miss for the defects that we thought would be there. But we did take it a little bit further in that we made the samples, and then we did look at them with serial sectioning before and after heat treatment, as far as what is going to happen to these defects. So a lot of the defects, pre-heat treatment, were definitely visible, so we should have been able to see them in CT. But what they do is they actually close up a little bit, making it harder for our CT systems to see them. And that's kind of why we didn't end up seeing them in the CT systems to begin with. So it's an interesting conundrum, when to do the CT. You're probably going to want to do it, at least for computed tomography, before you do your heat treatment, because it will close up the pores and create some interesting issues. So as we kind of move forwards, we certainly realize that we don't want to do computed tomography for everything. Even though these super complex geometries kind of lend itself to CT, but it's prohibitively slow. So generally, even a fast CT system is going to be a couple hours to get the data that you need. So for production, that's just not going to work out. And plus, deploying a CT system to space. Well, we've got a concept, and I'll show it. But still kind of interesting. So we started working at how do we go down the path of, trying to get some of these other things that we normally use in traditional NDE working. So trying to just help generally on X-ray and X-ray tomography. We've got some image quality indicators, and I'm going to show you those in a minute. We did a lot of work in nanopenetrates to help improve for crack detection. Certainly, and this is one we're still working through, is establishing probability of detection, which goes a lot into certifying any technique for fracture critical component. And part of the strength of a CT system is its consistent reconfigurability. You can put a CT system in lots of different configurations, but how do you relate a POD from one configuration to another is an interesting problem. And we're still working through that as well. We certainly looked at a lot for ultrasonics and found more issues than solutions, but both for the most popular phased array and full matrix capture. And again, we've been working on backscatter X-ray, the 3D X-ray for laser metal parts, which has shown some good results. Definitely put a lot of work into modeling and simulation, especially for these really complex parts. So can we make a simulation on a complex part so that we know where to put the sound in effectively to get a signal from a defect in a certain area of the part? And I'm going to talk a lot about that too. A lot of Monte Carlo based X-ray simulation, some automated intelligent defect finding. And a lot of what we're doing with all of this is trying to get all of this out through both kind of SAMP, ASTM, AS&T, and then the trilaterals and ESA for communication of the results that we're getting. Just trying to make sure that we're working through all of this, but then sharing it again back with the world. So if we talk about ultrasound, I put this one up there. It's very interesting kind of what happens, especially with the layering. So this was a block that we made on our freeform, which was the previous video that I showed. It's an electron freeform Sayaki machine that we have here at Langley. And you can see the block as built down here at the bottom. Certainly, you can see all of the different layers that were in there. But we intentionally put these defects in there and then machined it so that we could actually do the phased array and full matrix capture systems on it. But especially pre-heat treatment, what we found with these blocks is that you tend to get, at least in the phased array, these kind of regions where we're actually seeing layers and the grain structure show up as noise that is on the level of what an 1/8 of an inch flat bottom hole would be. The TFM system and the full matrix capture tended to do a little bit better, mostly because we could post-process out a lot of this work here. But certainly for certification for ultrasonics, especially pre-heat treatment, I think there's still a lot of work to be done with ultrasound. Although our initial results are pointing more toward full matrix capture versus phased array, which does make some sense because you can, in a full matrix capture system, you're effectively collecting every ultrasonic pulse that you could. Whereas in a phased array system, the phasing of the system has to be set up ahead of time and just caused us some interesting issues. I'm not saying by any means that they can't be tackled. They're just still in work. So one of the questions that became an interesting one and that we're going to talk about here for just a minute is, so I was asked the question, well, how do we know which CT system in the agency is the one we need to use for certification of additive manufacturing parts, effectively asking which system is the best system in the agency. And at the time, we didn't really have an answer. So we started developing these image quality indicators specifically designed for CT. So you can kind of see all the designs here, and all of this has been, for the most part, made public, especially these ones I have on the screen here. But started printing these so that we could try to qualify our CT systems using a known geometry. And then what we found was a lot of the printers couldn't print below what the resolution of the system was, so we started adding extra line pair gauges inside the IQIs to do that. But you'll notice none of the edges line up. And this is a pyramid that should go to a point. So you effectively have your three-dimensional version of what the normal X-ray line pair gauge would be, which is pretty cool. And I'm going to talk a little bit more about this in just a minute. We did do some development in nanopenetrance and use some Magnaflux particles, which actually worked out pretty good. And I apologize for not having a shot of that work on here. But again, the reference is at the bottom of the screen. And we're still working through this probability of detection. Currently at Marshall Space Flight, working on Inconel, especially for CT. So one of the interesting things that happened, we were talking with our folks here at the wind tunnel, which is a really nice marriage for us because the folks that work here, so NASA Langley, excuse me, has several wind tunnels, but making additive manufacturing parts for them is a critical function because they can design and iterate and put it in the wind tunnel, and it's smaller parts and it doesn't need to meet the man rating that we normally would have for fracture critical. So they can iterate and design a lot faster than we could if we were trying to actually do, additive manufacturing parts for spaceflight. We showed them the IQI and they actually started using it, but made this really interesting modification in that they put these spheres in here so that they could intentionally trap powder during the build. And they actually use it as a traveler. So we can have a record that is an image quality indicator for CT that actually has the powder that was originally put in the build trapped in there. And that way, if anything goes wrong, we can actually cut the IQI open and see what was actually put into the build that was the powder that was put into the build as a secondary check kind of down the road. So we've also been working a lot toward modeling and simulation. And I'll specifically, we have a team here that's doing physics-based modeling for lots of different things, especially for additive manufacturing and carbon composites. But we made a decision a couple of years back to make SIVA available agency-wide, and we actually serve it up here from Langley. So we made a full-on move into being able to make NDE simulation and analysis packages available to everyone agency-wide, and it's starting to have some really interesting implications. It wasn't just, it ended up not being just used for looking at how we would apply NDE to additive manufacturing parts, but one of the researchers here is actually turning it into a tool that can provide a design for inspection simulation. So effectively a tool that we could give to designers as they're building things to say, how inspectable is this part? And it has a score that it gives you so that designers can iterate, I won't say without the NDE folks, but to help design more inspectable parts down the road. So I'm going to shift a little bit here, and you guys heard me mention it at the beginning. And I put this in here specifically just so the people that are aware. So we do have an SBIR, or Small Business Research Initiative program, that NASA Langley runs, and we interact with thousands of businesses every year. In the NDE, it's generally about 50 a year that we'll get through the phase 1s and phase 2s. But you can see the dollar amounts here. And so we've been at it for quite a while now. And just for NASA, we have approximately, I think it's on the next page, but so this is just 1 year for NASA, the SBIR program. There's about 409 different technologies in different areas. And they do have specifically in space things, as well as, building things out of regolith and all kinds of different things. So if you're looking for a place to interact with NASA, I highly suggest you look at it and take it under consideration, because it's a good place to have an inroad to start working some of these issues along with us. And this programmatic call comes out every year, and there is a lot for in-space manufacturing and additive manufacturing, although, as I mentioned, it's not limited to that. So as far as the NDE section goes, since 2010, we've had over 68 phase 1s and phase 2s, which totals, I think, somewhere north of, I think, $10 or $12 million investment that we've made. And these are just some of the examples that we have. So this is actually the second generation of the backscatter unit that sits here. That's actually mounted to a Fanuc robot and was built with us in Physical Optics Corporation. And as you saw, so what we're going to do here at NASA is I'm going to find the person that's the subject matter area expert in your specific NDE technology. They'll be the person that's reviewing the proposal. And then eventually we're going to try and connect you up with a program that needs that technology at the appropriate center. And I will say, we're operating from all 7 major centers. So you may end up at Kennedy, you may end up at Johnson, you may end up here at Langley. And I'll point out this other one. So this is a really neat one. This is actually a heterodyne mapping system for surface acoustic waves, but it puts out the array. So in the normal ones, you have to take each point at a time. This one will map the whole surface all in one shot, which is pretty cool. And again, looking for in space, this is what the part of the reason that we're choosing some of these is because we can deploy these out into space, because this one's laser based and this one's X-ray based. So kind of cool. So I'm going to talk a little bit about human spaceflight support and some of the different things that we've done over the years. So on orbit NDE is not a new thing. We've had a lot of different applications over the years. This is actually the IR camera shots, the qualification shots for the camera that's up on the space station. We have had and had on shuttle an acoustic impact detection system, as well as long-range thermography of the shuttle to actually look at the heating of where it is. And one of the interesting applications that we actually had for the IR camera was looking at the ISS radiators during an issue that they had. So this is kind of the past. But more in the present, so we actually had a leak on the space station that was discovered on the Russian side. And the story of how they found it was pretty interesting. They actually closed up the module and let some tea leaves go. And eventually the tea leaves kind of migrated to where the crack was. But we actually were able to get an eddy current inspection system up on orbit, qualified with the astronauts, and delivered it to the space station. And they actually did and were able to, examine the crack in the wall and be able to make sure that it wasn't a surface crack and actually pinpoint the ends of it and get that done for the space station. So pretty cool that we were able actually to do some in-space inspection on the space station. And certainly as the space station gets older, we're probably going to have more of these issues that we need to deal with. So you've heard me talk about it, and especially the Goddard team working with Marshall Spaceflight is looking at NDE for, in-space manufacturing, so building of additive manufacturing parts in space. So we kind of started with this, which is establishing key parameters for how you would actually develop these systems. So this is a nice little gear that we were building with a polymeric system that was it's not a sintered material, but it is heated. But putting intentional cavities and voids in there, and then looking at them with the CT system, and looking at what kind of voids we should expect from those systems. So we went to the next design iteration of that, of actually performing the kind of design ideation team of being able to build a CT system for space. So this was the design iteration that came out. It's a rack mount CT system that we could actually send up to the station and deploy. So this was completed through the IDL, and all of the subsystems have been worked through, but also working with a commercial partner, Northstar, to help do that. But in addition to that, we've also started to help, work with Aerospace Corporation to explore what they're calling an open CT concept. And it allows for self-determining geometries for different things that we might be able to do. So we're thinking about larger structures that might be built in space, so that we could actually just take X-ray shots and be able to turn that back into some sort of computed tomography type data. Again, these are somewhat concepts at this point, but just us trying to look forward into how we would actually perform some of these inspections in space. So certainly, if we start looking at in situ resource utilization, there's a lot going on, and a lot of it is put around regolith and building things out of the dust that's on the moon already. And this spans everything from, launch pads to walls to MMOD production. And a lot of that future effort will have to have some NDE to be able to look to make sure that the structures that we built were built the way that we thought that they were. So motivations for doing it, certainly there's a lot of hardware and quality. So if we actually start building additive manufacturing parts up in space, we're going to want to make sure that they were built correctly. There's certainly a lot of, we expect once we start doing that, we are expecting to have some failures, and we're certainly going to want to be able to do those failures analysis in real time, because we're not going to be sending those parts back. Certainly mission safety is a critical thing for NASA. In-space manufacturing, in situ resource utilization. And actually the one that's kind of interesting that's kind of come up more recently is, if we're doing science initiatives on the moon and we're picking up rocks, we would like to be able to do the sample triage without return. So we would like to know what's inside of those systems, inside of those samples, without actually having to send them back to Earth. So again, computed tomography comes up as kind of a primary, but we are looking at others as well. And here's some of the more positive results that we've gotten so far. And I appreciate Joe Zalameda, and he actually presented this at one of the SAMPE things, I believe. But this is actually a piece of lunar regolith that's been polymerically binded. And we put intentional defects at it and started looking at it with just thermal and heating up the samples. And effectively for in space, we would be using the sun most likely as the heating source, but certainly able to pick up voids and defects within the sample using IR, which would can both be done as an inspection technique, but also kind of a local as well as in long distance, as we saw with the long-term or the long-distance mapping of the heat shield on the space shuttle. So this is kind of the last one I'm going to cover, and it's a little bit deeper than the others, but we ran into an issue with Clario. So if you guys don't know what the Clario mission is, it's basically the next generation for the mapping of the atmosphere that's going to go up and be on service on the International Space Station. And we ended up having an issue with this flex harness, which was the direct connection between the sensor head and the gimbal that it sits on. So as you can see, it's putting out a swath there, but it gimbals back and forth. And effectively, when this is attached to the space station, we should be able to map most of the atmosphere within every 2.5 hours or so. So certainly going up and high. And if you want to read more specifics about that, this was the IPX technical paper of the conference in 2022. So when it comes to the NDE, they sent the flex harness up to us here, and again, failing at almost 10% of life. So we started going around trying to find NDE techniques that we would implement to find some of the damaged areas in the traces. And this is kind of what we came up with. So mostly doing digital X-ray, but failed to find any areas of interest on the ribbon, CT, and then IR as well. So I'm going to cover all that here in just a minute. So what we ended up doing with the IR is we actually were able to get very small 5-volt pulses, because I didn't want to damage the harness itself, into the wiring of the harness itself. And where there was a little bit of incipient cracking, because these wires weren't broke, they were just not transmitting the way they were supposed to. I actually was able to get it to heat up just a little bit, and I could map that with our IR camera and go in and pick out all these little areas on the different traces, so that I could go and then cut them out to do something a little bit more high resolution.
Hey, Eric, I'm just going to give you the 5-minute warning.
All right, I got you. Yeah, we're going to get there. That's perfect. And it's good to hear somebody's voice so that I know I'm not talking to myself. So anyway, one of the things that we did notice in the harness was that some of the traces were a little bit darker in X-ray than the others, but initially it didn't seem to really be something of interest until we went just a little higher, and now we can certainly see some big variations in the wires and where they're located. This is our large area CT system that we have here at Langley. So we actually laid out the harness full flat and started to work through it. And what we actually ended up finding, and it may be hard to see through the screen, but lots of little incipient cracks on the different traces, but they weren't in the thicker traces, which was a lot of interest to a lot of the people that were working this problem. But we actually went in and cut out these small samples based on the IR signatures, and that's how we were able to get down and actually find these incipient cracks in the wiring harness. So I don't know if this one, yeah. So got a nice little, so probably easier to see. So the cracking is definitely all on one side of the harness. And what we ended up noticing from the CT is that one of the set of the wires was a lot thicker on the other side than on the other side, by about 25%. And that's what actually led to the root cause of the problem, is that it created sort of an I-beam effect that's on the last slide. So, but one of the recommendations we were able to say, so you can see just by X-ray mapping, once you know what the problem is, it's pretty easy to see where it occurred, because these traces are much darker here and attenuating more X-ray versus the rest of the wiring harness, which was all nominal thickness. And we actually found out later on that what they did was they had actually folded this harness over, and just this part had been plated a little bit more than the rest, which eventually created this I-beam flex problem, which is kind of interesting. So in a flex harness, you actually want to have not aligned like this, but non-aligned, and as well as similar thickness, so that the strains on the both sides of the wire are not causing a stress in the thinner wires. Again, if you want to read more about it, this was the APX paper of the conference, and kind of a neat application for NDE for our next set of missions, which are going up to help atmospheric mapping. So, in perfect timing, I'll say, for the most part, there are a lot of different ways and opportunities to collaborate with NASA. I've got them all listed on here, at least the ones that I'm aware of. And we certainly have, and if you get the slides at the end, there's some stuff in the background. We've been putting out models specifically for 3D printing that are NDE specific, have some interesting anomalies in them to you, so you can actually go, and especially for the universities, designs are done. All you have to do is print them out. They are a little bit NASA centric in that if you're doing the NDE right, there is a NASA meatball that you can see that you can't see nominally. But again, I'll point out our SBIR program, as well as the OSMA program, and then Artemis and the others. And with that, I will turn it over for questions.
Eric, that was great. Thank you so much. I actually wrote down a ton of questions. I think a lot of them I'll have to reach out to you independently.
Yeah, no problem.
But I think it was also great not just to kind of present some, great things you guys are doing, but having the references. I think having the references for people to dig deeper, and then the SBIR, and how they can kind of connect with NASA is great kind of synergy between NASA and SAMPE. So I appreciate you making those connections. So just a reminder to folks, put any questions in the Q&A. We have a few here, so I'll get started. The first one is, what was the AVCode bonded with? Can you expand more on how the inspection process helps verify the bond integrity?
Yeah, so there was two, and I'll flip back to the side. So I can't tell you exactly what they used, but at the same time, essentially it's like a mastic, right? So it was effectively, if you've ever tiled a floor or something like that, there was a mastic that goes down, and then the AVCode tile blocks are pressed into that mastic. And so what we really wanted to be sure was that the mastic itself had adhered well. And that was done by the two methods that we talked about, right? So the terahertz is covering the block acreage and looking for any major problems that would have occurred at that bond line. And then, of course, the actual bond verification was the ultrasonic technique, where you're using a stress wave that's going to have an issue where there isn't a mechanical connection to come back. And the terahertz is more sensitive spatially than the ultrasonic technique was, because of the attenuation of the AVCode itself and how deep it was. So some sections of the AVCode were pretty thick, and getting sound down into that was not the easiest thing in the world. So, and a lot of credit to aerospace for coming up with the technique and helping us get it deployed.
Thanks. This was the phased array system and immersion system.
Is there a question?
I'm sorry. Was the phased array system an immersion system?
It was not.
Let's see. Is a flaw that closes up after heat treatment with HIP or not still considered a concern if CT misses it? And how do you then quantify?
So these are the questions that we go to fracture control with, right? Yeah. So, I do have a materials background. So the answer is, for the most part, yes. So from an NDE standpoint, it's a definite, right? So if there's still a defect there, but it's below what I can find, then, you kind of got to talk out of both sides of your mouth, right? So there is an inspection criteria that basically says, a critical defect of this size is what you need to find. And that's how it's done. And NDE techniques have to have some place to go in order to get qualified. So that's typically how we go at it from that point of view. The problem is, if you know there's a defect there and you know that you can't see it, does the problem go away? And the answer is it depends, but not usually.
Yeah, there's probably a lot more to say on that one, but
yeah, that's the chicken and the egg argument that we have all the time.
Next question. You mentioned toward the beginning that Monte Carlo simulations were used regarding X-ray. Would you be able to elaborate on the type of Monte Carlo used and the random variables considered?
So for the most part, we were flushing out a system at the time. So most of this, and we've actually done a lot more. It's just not in the presentation. But the Monte Carlo does allow you to do a lot of things as far as spatial resolution. How many X-rays do you need to take in order to get a valid CT? And we did do it both with ultrasonic and the X-ray. Just to kind of flush out the system. But now it's moved a lot more toward that design for inspection, where we can run through different inspection scenarios and say that we think that this is going to be inspectable or not, and using it that way. But the variables depend on which inspection technique you're talking about. So specifically for X-ray, it would have been mostly magnification and energy, and trying to work through that, and specifically for CT. So that was kind of where we were working at that time.
Thanks. I think the last question here. You mentioned alternative methods to X-ray CT, such as UT and backscattered X-ray. Is NASA thinking of other bulk inspection methods for manufacturing, such as resonant acoustic methods? Maybe as a stage 1 inspection method, then go with stage 2 higher resolution methods.
Yes, definitely. And in some of the other presentations, this is a stripped down version of a lot of different sections, but we have definitely been looking at and having fairly good success with some of the resonant techniques, and specifically for, so at least here at NASA, so there's kind of two things to this, right? So if you're going to go after one of the resonant techniques, you really got to want to do a lot of parts that way. And so sometimes it's a little bit cross prohibitive from NASA's point of view to make that happen. So, but we have done it, and specifically with fasteners. So we do go through a lot of fasteners, and especially a lot of this work's being done at Goddard. But we have been able to show good correlation, and both with regular parts and additive manufacturer parts, especially after heat treatment in the resonant technique. So there's definitely something there. But as I said, generally part of the problem and the reason that we don't tend to want to go to a resonant technique for a lot of different things is just that we don't usually make enough of them. So you have to establish the statistically relevant parameters, and you got to run through a lot of parts to do it. So, if we had a case, and fasteners is a really good case, where we can have enough of those parts. And actually the one study that's going on, we were actually able to tell which lots certain bolts came from. It was that sensitive. So an excellent question. Definitely resonant techniques, very good. I apologize for not mentioning it in here, but we are looking at it, and it is seeming to be a very positive result, at least thus far.
Awesome. Well, Eric, thanks again for participating. I know it's kind of a, added extra thing, but I think it was a great talk. And again, I think the SAMPE talks for this TC have been good. I judge that by how many people stay on from initial slide to last slide, and you did great. I would like to share my screen, I guess. Give me one sec here. And just kind of remind people, I guess, of TC7. We're looking for people to join. You can kind of reach out to myself or Jayden via email to join TC7 and SAMPE. Why we're really, this is a great example. Make connections, that could be beneficial. to solving a problem, or again, just meet new people in the industry. So we look for your help. We have one more webinar next month. Allison Park will be talking about additive manufacturing, so please look to register there, and I hope to see you join that webinar. And then the following month, we expect to have more of a sit-down discussion based on some recent survey results of what topics folks sound interested in. So thanks for your time, and we hope to see you next month. Thanks again, Eric.
Yep, no problem. Thank you, everybody. Have a good afternoon or end of the morning.